Hello everyone, welcome back. In this video we're going to talk about planes in three-dimensional space. One of the first things we're going to talk about is what set of information uniquely determines a plane in three-dimensional space, and from that we'll figure out how to represent the equation of a plane using vectors or a scalar equation. So recall when it came to lines in three-dimensional space, we saw that 2 points in space uniquely determined a line, and well, for planes it's going to take 3 points to uniquely determine a plane. Well, it's going to take 3 points to uniquely determine a plane as long as those 3 points do not all lie in the same line. So a plane can be uniquely determined by 3 points in space, but a better set of information that uniquely determines the plane is a single point the plane goes through and a vector that is normal or orthogonal to a plane. If we think of my hand as a plane, remember a plane is just like an infinitely big flat piece of paper in three-dimensional space, then the normal vector is the vector that comes out orthogonally from our plane at a 90-degree angle, and it gives us the orientation or tilt or angle of our plane. So a plane is uniquely determined by 3 points that are not aligned or lying in a single line, or by a single point in a vector that is normal or orthogonal to our plane. And it's really that second set of information that uniquely determines a plane that is going to help us create the vector and scalar equations for a plane. And so let's go ahead and look at the picture of a plane that I have drawn over here. So n is representing that vector that is orthogonal to our plane, or what we're going to refer to as the normal vector to our plane. P naught is a known point that our plane goes through. So maybe that point will have coordinates of like x naught, y naught, and z naught. And P is another point that is in our plane, and this point is an arbitrary or random point that we can think of as having variable coordinates of just x, y, and z. And so really important observation that we need here to help us create this vector and scalar equation of a plane is the fact that this n vector is normal to every and all vectors that lie in our plane. And so one of the things we learned about vectors that are orthogonal or meet at a 90-degree angle is that their dot product is always 0. So if we find a vector that lies in our plane, like the vector that starts at p naught and goes to p, and we take the dot product of that vector in our plane with our normal vector to our plane, that dot product is always going to be equal to 0. So the vector equation of a plane is given by this dot product formula that we see here. It's the normal vector to our plane dotted with any vector that lies in our plane, and that dot product is always going to give us the scalar of 0. So this is the vector equation of the plane, and if we assign components to our normal vector and this vector that lies in our planes, we can create the scalar equation of our plane. So for our normal vector n, we're going to suppose that it has components of a, b, and c. And the other vector that lies in our plane, we can find its components from how we labeled these points p naught and p. So the vector from p naught to p will have components that are just made up of the differences between the corresponding coordinates of these 2 points. Remember, if we're having a vector that starts at p naught and goes to p, the first component is found by taking the difference between those first coordinates. That'll give us x minus x naught. And to find the second and third components, we do a similar process. Just take the difference between the second and third pairs of coordinates. So our second component will look like y minus y naught, and the third component to finish it off will look like z minus z naught. And so now if we go back to the vector equation of our plane, n dotted with the vector from p naught to p being equal to 0, if we plug in the components of these vectors that we have now labeled, we can create a scalar equation for the plane. So let's go ahead and check that out. So we're going to take the dot product between our n vector, which has components of a, b, and c. That gets dotted with our vector from p naught to p. That's x minus x naught, y minus y naught, and z minus z naught. And we know that that dot product is going to be equal to 0 no matter what point x, y, and z in our plane is used in this process. So we can actually think of the plane as the set of points x, y, z that satisfy this equation. So this is still really the vector equation of our plane, and it's still involving vectors, but if we compute this dot product, we know the dot product will give us a scalar, and that'll help us go from the vector or dot product version of the equation of our plane to the scalar equation of our plane. So remember, to evaluate a dot product, we just multiply the corresponding components together and then take the sum of those products. So if we multiply the first components together, we'll get a times x minus x naught. We have to add to that the product of our second components multiplied together. That'll give us b times the quantity y minus y naught. And to finish this off, we have to add on to our first two terms here the product of our third components, which will look like c times the quantity z minus z naught. And remember, this dot product is equal to 0 as long as x, y, and z are a point that is in our plane. And so this is the scalar equation of a plane in three-dimensional space, and this is kind of like our point-slope form for a plane if we want to think about an analogy back to lines in two-dimensional space. So remember, in this setup, a, b, and c are the components that come from that normal vector to our plane. X naught, y naught, and z naught are known points that lie in our plane, and x, y, and z are variables or representing the unknown points in our plane. And so oftentimes we'll actually work with an expanded version of this equation. So if we take a moment to expand out this really general formula for the scalar equation of a plane, well, we'll see what happens. Well, let's look at the variable terms first. So that'll look like ax plus by plus cz. Those are our three variable terms. Every other term is technically going to be a constant that we could combine together if we knew the values of a, b, c, x naught, y naught, and z naught. If we finish using the distributive property to expand everything here, the rest of the pieces would look like negative a times x naught minus b times y naught minus c times z naught, and all of that will still be equal to 0. So if we do know those values and take the time to combine these constants together, another common way to write the equation, the scalar equation of our plane, is going to look like ax plus by plus cz plus d is equal to 0. So a, b, and c are still representing those components of our normal vector to our plane, and now d is representing the scalar of negative ax naught minus by naught minus cz naught. And so another way that you might sometimes see the equation of a plane represented is as ax plus by plus cz is equal to some constant, like we move that d to the other side. We have to be really careful and mindful when we're pulling values and numbers out of the scalar equation of our plane, because depending on the problem we are trying to solve and the formula we are using, it might require the equation of our plane to be written in a very specific way. So keep your eye out for that when you're solving problems later on. If you're trying to pull values out from the scalar equation of a plane to plug into a formula, make sure your equation of your plane is in the right form that the formula requires. So just to summarize that last little discussion, we know the scalar equation of a plane can be written in two forms. The a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0 form. Or if we expand this out and combine constant terms, the scalar equation of a plane may also look like ax plus by plus cz plus d is equal to 0. So as long as we know a single point, x naught, y naught, and z naught that our plane goes through, and the normal vector to our plane with components of a, b, and c, we'll be able to piece this information together to create the scalar equation for our plane. So in this example, we're asked to find the equation of the plane that goes through the three given points. Those points are P, Q, and R. Our point P has coordinates of 1, 3, and 2. Q has coordinates of 3, negative 1, and 6. And R has coordinates of 5, 2, and 0. So taking the time to really accurately plot these 3 points in three-dimensional space or on a set of three-dimensional axes is not necessary to get through this example. I'm just drawing a little picture over here to help visualize the concept that we're going to use to figure this problem out. So in our earlier discussion, we also came up with this scalar equation for our plane. A times the quantity x minus x naught plus b times the quantity y minus y naught plus c times the quantity z minus z naught will be equal to 0. However, this equation was not constructed by using 3 known points our plane goes through. It was constructed using that other set of information that uniquely determines a plane. Remember, the other way we can uniquely determine a plane is using one point that we know the plane goes through. That's the point with coordinates of x naught, y naught, and z naught, which we have here. We actually have 3 of those points, and we can use any of them that we want. The other piece of information that we don't have yet is the vector that is normal to our plane. That is our vector with components of a, b, and c. So what we're going to do is use these 3 known points to create a vector that is normal to our plane. And the way we go about doing that is by taking these points and finding the vectors that go from one point to the other. So we could do the vector from P to R and the vector from P to Q, or we could do the vector from Q to R and from Q to P, or from R to Q and from R to P. Any combination here is going to give us the same result in the end once all the dust clears. And so now the really important observation that we need to make here is that we know these vectors that we created here, like the vector from P to Q and the vector from P to R, are both going to lie in our plane. So if we think of like my hand as our infinitely flat plane, maybe our vector from P to Q looks like this. Maybe our vector from P to R looks something like this. Both of these vectors definitely lie in our plane though. And one of the things we learned about the cross product is that if you take the cross product between two vectors, it's always going to give you a vector that is orthogonal to those two vectors. So that means if we take the cross product between these two vectors that we just created, the vector from P to Q and from P to R, that will always give us a vector that is orthogonal or normal to both of those vectors. That means that vector will be our n vector, the vector that is orthogonal or normal to our plane. All right, so what does our vector from P to Q look like? Let's find those components. And remember, we can always find the components of one of these like displacement vectors, or the vector goes from one point to another, just by taking the difference between their corresponding coordinates. So the first component of our vector that starts at P and ends at Q will be found by taking the difference between the first coordinates of our ending point and our starting point. So that'll give us 3 minus 1, which is 2. To find the second component, we take the ending point's second coordinate and subtract away from it the initial point's second coordinate. So that'll give us -1 minus 3, which is -4. The third and final component is just found by taking the difference between those third coordinates. That'll give us 6 minus 2, which is +4. So our vector from P to Q is going to be 2, -4, 4. We also need another vector that lies in our plane, and we said we are going to use the vector from P to R. Well, the vector from P to R is going to have a first component of 5 minus 1, or +4. The second component of the vector from P to R will be 2 minus 3, or -1. And the third component will be 0 minus 2, or -2. And this normal vector is kind of uniquely defined in our plane, but it's not necessarily a unique vector itself. Really, the normal vector is coming from a set of vectors that are normal to our plane, but all those vectors that are normal to our plane are going to be parallel to each other. So we might get a vector that points up and out of our plane like this if we take a certain cross product. A different cross product using different vectors that are still in our plane may give us a longer or shorter version of that normal vector, or especially if we switch the order of our cross product, our normal vector may point down instead. And so that's something we have to look out for. If we're kind of comparing planes later on in their normal vectors, we might recognize, well, if they're just a constant multiple of each other, they are going to have that same normal vector, and that will tell us something about the relationship between those two planes. But the takeaway we need from that for this example is we might have a different output from this cross product depending on the vectors we use. That might give us a different looking normal vector to our plane, but it's really going to be parallel to any other normal vector we may compute from a different cross product. Once we plug all this into our scalar equation, expand everything, combine like terms, and adjust for signs, when all that dust finally clears, no matter what normal vector we use, we're going to get the same exact scalar equation for our plane. All right, so now let's go ahead and finally find our normal vector n. And to find our normal vector to our plane n, which will give us our a, b, and c values, we have to compute the cross product between the pq vector and the pr vector. And so remember, one way to compute a cross product is using a 3x3 determinant. The top row of our 3x3 determinant, we place the basis vectors I, j, and k. For the second row of our determinant, we enter the components of our first vector, the pq vector, and those components were 2, -4, and +4. The final row of our 3x3 determinant comes from the components of our second vector in our cross product, our PR vector, which has components of 4, -1, and -2. So let's first find the I component of our normal vector. And so we're going to start at I in our 3x3 determinant and look at the constants that we run into as we move along the right diagonal, going down and to the right from our starting position. So we'll hit -4 and -2. The product of those constants will give us +8. And we have to subtract away from that the product of the constants that we get by traveling down the left diagonal that starts at I. And remember, as we move down and to the left, if we go outside of our 3x3 determinant, we have to wrap around. So the left diagonal that starts at I will give us the constant that comes from the product of 4 and -1, and that'll be -4. So to find the j component of our normal vector, we're going to start at j in our 3x3 determinant and move down that right diagonal. And so we're going to have to wrap around again, but as we move down that right diagonal that starts at j, we're going to have the constant factors of 4 and 4 that get multiplied together, and that gives us a 16. We have to subtract away from that 16 the product of the constants we get from the left diagonal. And so that left diagonal that starts at j will hit 2, but then as we move down and to the left again, we're going to have to wrap around and eventually hit that -2 on the other side. So that left diagonal gives us 2 times -2, which is going to give us a -4 we have to subtract from 16 to finish computing our jth or second component. And so for the third and final and kth component, we're going to do this process one more time, but now we start at our k unit vector and move down and to the right. That right diagonal will give us the product of 2 and -1, which will be -2, and we have to subtract away from that the product of our left diagonal that starts at k, and that left diagonal that starts at k will give us -4 times 4, or -16. And so now we can just simplify this a little bit, and we can see that our normal vector n is going to have components of, well, 8 minus -4 is +12i, 16 minus -4 is +20j, and -2 minus -16, or -2 plus 16, is going to give us +14 times k. And so through this cross product, we have found this vector that is orthogonal to our plane, and that's the missing piece. Now that we have this normal vector a, b, and c, and we know a point that our plane goes through, we can put all that together to construct the scalar equation of our plane. All right, so now we have the set of information that we really need to construct the scalar equation of our plane. Our normal vector n has components of 12, 20, and 14. We need that to construct the scalar equation of our plane that gives us a, b, and c. And we also need to use one of the known points that our plane goes through. And it actually doesn't matter which of these known points we use. If we expand and collect the constant terms, it's all going to give us the same exact scalar equation in the end. And that's also true if we were to use a different normal vector to our plane. If we used any constant multiple of this vector, when all the dust cleared and we expanded and combined everything and simplified it, we'd get the same scalar equation of the plane, even if we used a different known point in our plane or a different but parallel normal vector. But using the normal vector we came up with and the known point of 1, 3, 2, the scalar equation of our plane is going to look like a, or 12, times the quantity x minus x naught, or x minus 1. Then we add to that b, which is 20, multiplied by y minus y naught, which will look like y minus 3. To finish this off, we add to this c, or 14, times the quantity z minus z naught, which will look like z minus 2, and all that adds up to give us 0. And so we do have a scalar equation for our plane, and this is kind of like that point-slope form for a plane. So here's our point, and now the slope of our plane is really given by these coefficients of a, b, and c. So while we do have a scalar equation for our plane, it might be more convenient to write it in that other form where we expand and combine all the constants together. So if we do that here, our variable terms are going to look like 12x plus 20y plus 14z. And then our constant terms from the rest of the distribution here are going to be a -12 from our first piece, a -60 from our second piece, and a -28 from our third piece. And so we can't combine the variable terms together. They're 12x plus 20y plus 14z. But we can combine those constant terms together, and -12 minus 60 minus 28 gives us -100. And so another scalar equation for our plane that's equivalent to the first one is 12x plus 20y plus 14z minus 100 is equal to 0. We could recognize, well, everything here is an even number and there's a common factor. And so if we do simplify this by canceling that common factor of 2 that is present in all the terms and coefficients, we can rewrite our scalar equation as 6x plus 10y plus 7z minus 50 is equal to 0. And so we have found the scalar equation of the plane that goes through the 3 points that were given, P, Q, and R. And just to recap our process, remember the first thing we did was we used our 3 known points to create these 2 vectors that lie in our plane. We took the cross product between those 2 vectors to find the vector that is normal to our plane. Once we had our normal vector, we used our normal vector and one of the given known points our plane goes through to plug into the general equation for a scalar equation of a plane. We then just simplified our formula and got our final answer of 6x plus 10y plus 7z minus 50 is equal to 0.